Hey everyone, welcome back to Probability Theory. This will be lecture 15 of the course. And in this section, we're going to be discussing the binomial probability distribution. So let's go ahead and jump into it. And we'll call this section 2.4, the binomial distribution. And so we talked about what a probability distribution is, and what we'll plan to do for the next handful of lectures is explore the common distributions that are appropriate for undergrad probability. And so we'll begin with what's called the binomial distribution. Now, what do we mean by these common distributions? Well, we kind of think of these as named distributions. And we've got things like the binomial, the geometric, Poisson, normal, etc. There's a bunch of them. And so what are these things? Well, they're basically standardized probability models that describe how random variables behave under specific, commonly encountered patterns of randomness. Now, each of these is going to have a name, right? And associated with them, there's going to be sort of a characteristic shape of the histogram of the distribution. There's going to be sort of parameters that each of the distributions have. And so we'll get into all of that in this lecture. But just know that this is the first in a series of lectures that will explore these common distributions. A lot of what this class is about is exploring these commonly encountered patterns of randomness and being able to generalize them. Okay, and so the first distribution we want to talk about is what's called the binomial distribution. Okay, and so the idea behind the binomial distribution is this. Some experiments consist of sequences of identical and independent trials. All right, so we're talking about identical and independent trials. Right, so think of like flipping a coin in a row, right? So, like flipping a coin repeatedly. Okay. In addition to having identical and independent trials, the binomial distribution requires that each trial has two potential outcomes. So each trial has two potential outcomes. Think of this as like a yes or a no, or an on or an off, or a success or failure and success. Or in the case of flipping a coin, something like a heads or a tails. Okay. Right, so e.g. these things. Okay. And so this is the kind of scenario that would, make us want to think about using a binomial distribution to quantify probabilities. Right, so let's kind of get a concrete example out in front of us, and then we'll dissect it a little bit more. So let's let x be a random variable denoting a yes if the flip of a coin is heads, and a no if the flip is tails. Okay. All right, so you got a random variable denoting a yes if the flip is a heads, and a no if it's tails. Right, so if we do this 20 times, say we flip a coin 20 times in a row. So if we flip the coin 20 times in a row, we would get something like, like a, maybe, I don't know, heads, heads, tails, tails, heads, tails, dot, 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 whatever, tails and heads, right? And so, you'd say, well, if I get a heads, that's a yes. If I get a tails, that's a no. All right, so something like this. right? And then there would be 20 of these, right? Okay, so this is the kind of situation, right? So think about what we're doing here. We're doing identical and independent trials, right? Each trial is a flip of a coin, right? We do 20 of them, okay? And each trial has two potential outcomes, either a heads or a tails, a yes or a no, a success or a failure, depending on how you define these things, okay? Okay, so this is an example of a binomial situation here, or a binomial experiment. Basically doing something over and over again that, identical trials, independent, with two potential outcomes. That's a binomial experiment. Okay, let's do one more example just so we can kind of get some, we want to get a physical sense for like what these things look like. Here's another example. So in this case, let's let x be a random variable. Let x be a random variable denoting yes if the flip of a coin, yes if we roll a die that produces an even, number, and no otherwise. Okay, so x is a random variable that's either yes or no. It's yes if when we roll a die we get an even number. It's no if we roll a die and we get an odd number. Right, so let's say we do this 100 times. We might get things like 2, 5, 3, 3, 1, 4, so on, 6, 4, right? Right, so these are all the potential outcomes of rolling a die, right? 1, 2, 3, 4, 5, or 6, fair 6-sided die. And so you'd have a yes here, a no there, another no, another no, another no, and a yes, and a yes, and 2 yeses here, right? And so if you did this 100 times, you'd have like a string of yes, no's. Okay, this is another example of a binomial experiment. A binomial experiment. All right, let's go through the checklist. We've got independent and identical trials. Each trial is just rolling a die. Right? The way we've defined the random variable x, it's either yes or no, right? Even though there are technically 6 potential outcomes, 3 of them correspond to yes, 3 of them correspond to no. Okay, so there's 2 potential outcomes, right? And so this is another example of a binomial experiment. Okay, so let's kind of formalize the idea of a binomial experiment. What does this mean? So properties of a binomial experiment, right? So we kind of went over them, but let's make sure we've got them all in front of us here. So there's a few others, right, actually. So number one, the experiment has a fixed number of identical trials. Has a fixed number of identical trials. Okay, and the fixed number, we'll say n. I'll just put it here. We'll use the letter n to denote the number of trials. And we'll see that this is actually one of the parameters of the binomial probability distribution. Okay, so we've got the experiment has to have a fixed number of identical trials. So in the previous example up here, we said we're gonna roll a die 100 times. So n equals 100. Right? In the experiment prior, we said we're gonna flip a coin 20 times. So in that case, n was 20. Okay, so that's property 1. So second property, each trial results in one of 2 outcomes. Okay, right? So you flip a coin, you're either going to get a heads or a tails. You roll a die, you're either going to get a even or an odd, right? And there's lots of other examples, and which we'll go through. We'll go through more in a second. But just kind of try to fix this in your mind here. Okay, so that's property 2. Property 3 is that the probability of success on a single trial is the same for all trials in the experiment. We just use the term success. That could be a heads, or that could be an even, or whatever, however you define it in the scenario you're looking at. The probability of success on a single trial is the same for all trials in the experiment. Right? So in the example of flipping a coin, probability of heads is 50%, right? And that is the same for every trial. It doesn't matter if it's the 3rd time I flip the coin, it's always 50%, right? In the example of rolling a die, the probability of an even is 1/2, right? It's 50%. Now, it just so happens, it's a coincidence that the probability of success is 50% here. That doesn't have to be. It could be 10%, right? So that is the 3rd requirement. Now we denote the probability of success using the small letter p. Right? And this is another parameter that we need to know in order to define our binomial distribution. Okay, so the probability of success is p. That means the probability of failure is 1 minus p. And we usually denote that using q. That's the probability of failure. Right, so if you know p, you automatically know q. Right, it's just 1 minus p. All right. Very good. So those are the first 3 properties. There's 2 more, right? We're kind of breaking the informal properties that we laid out at the onset. We're kind of breaking them apart a little bit. The 4th property is that the trials are independent. What do we mean by that? Well, like in the case of flipping a coin, right? It doesn't matter what I got on the previous flip or the flip before that. The flip I'm in the process of doing right now is completely separate from and uninfluenced by the flips that came prior to it. Okay, so the trials are independent. Same thing with rolling a die, right? It doesn't, the outcome of my die roll is not influenced in any way by the previous rolls of my die. Okay, so the trials are independent. They are not connected. Okay. And the 5th and final requirement is that the random variable of interest is the number of successes in n trials. So this is a new one. We haven't talked about this yet. The random variable of interest is the number of successes in n trials. Okay. All right. So the random variable x or y, whatever, it very specifically is keeping track of the number of successes in n trials. Okay, so let's do an example. Let's kind of put something more substantial here. So this will be the coin toss example. We flip a coin and mark it a success if we get heads and a failure if we get tails. Right, so we flip a coin, and we'll say we do it 20 times. N equals 20 times. Right, success equals heads. Failure equals tails. Right, and how you define these things depends on the context of the problem. Right, with the coin toss, it's completely arbitrary. It doesn't really matter. Right, and then we define the random variable. Let's let x be the number of successes in 20 flips. Okay, right? And so in this instance, we would say x is a binomial random variable. So x is a binomial random variable, right? Let's just confirm it, right? The first requirement was a fixed number of identical trials. So fixed number of identical trials, n equals 20 identical trials. Okay, so first thing, check. The second requirement was that each trial results in one of two possible outcomes, right? So each trial produces H or T, heads or tails, otherwise known as a success or failure. Okay, check. The third requirement was that the probability of success on a single trial is the same for all of the trials in the experiment. Well, probability of a heads is equal to, the success probability, which in the case of flipping a coin is 0.5. Okay. And so that means that the probability of a tails, which we would denote as Q, the failure probability, is 1 minus P, which is also 50%. Okay, so check, we've got that one. What was the fourth requirement? Well, the fourth requirement was that the trials are independent. Well, definitely that's the case with flipping coins. The coin tosses are all independent. All right, one toss doesn't influence the next toss and so on. Okay, and then finally, the random variable x itself, the random variable of interest, must count the number of successes in n trials. Well, that's how we've defined x. X is the number of successes in 20 flips, 20 trials. So x is the number of successes in 20 flips. Check. So we've got them all, right? So these 5 requirements are all met by our scenario of flipping a coin 20 times. And so we would say that x is a binomial random variable. We already wrote it up here, actually. All right, so that's the case. And so what we'll frequently do is we'll denote the distribution of x in the sense that it's a binomial distribution with the following notation. So we'll write x is distributed binomial, and then what we usually, binomial, B-I-N, and what we usually want to do is then list the parameters that are of importance here. And so the important things with the binomial distribution is you need to know the number of trials, so in this case 20, and you need to know the success probability, in this case P equals 0.5. Okay, and so this is the notation that we'll see whenever we have established that a random variable is binomial distributed. You might see shorthand x bin 20 comma 0.5, right? So that's the same thing, right? We're just leaving off the n equals and the p equals. Okay, but this is notation that you'll want to get used to. It's very convenient. Sometimes you'll have a range of random variables, or a group of them, and they may not all have the same distribution, and so you'll want to be able to label them. Okay, very good. Now let's talk through what the probability distribution of x actually looks like. Okay, so let's talk through the probability distribution of x. Okay, so we'll assume just 20 flips here. So n equals 20 flips, right? It's going to produce something like this. You're going to get a heads, tails, tails, heads, so on, heads, and there'll be 20 of them, right? This is just an example, right? You may get, there's going to be, one of the potential outcomes is all heads, and one of them is all tails, and one of them's 10 heads and 10 tails, and 9 heads and 9 tails, or 9 heads and 11 tails, right? So this is just an example of what this binomial experiment produces, right, for an outcome. Now, when the letter in the ith position, right? So the key here is that we're going to kind of switch to more general notation in a second here, but the position in the ith, the letter in the ith position corresponds to the outcome of the ith flip. Okay, right? So we can take these 20 coin tosses and the outcome, and we can sort of arrange them in terms like put all the heads together and put all the tails together. Because what we're really interested in is the total number of heads, right? And so let's say I get 8 heads and 12 tails. And so what I could do is I could rewrite this thing as heads, heads. So I've got, we'll say 8 of those, just for example, tails, tails, and I'll have necessarily 12 of those, right? Because there's 20 in total. Okay, so all I'm doing here is just kind of reorganizing these just for convenience. And we're just kind of building towards understanding what this probability must be. So we had 8 successes followed by 12 failures, we'll say in this case. Okay. And so again, you know, you could relabel these as S, S, dot, 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 S, F, F, dot, 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 F, right? And so there's 8 successes and 12 failures. Okay, again, 20. So how you label these things is sort of up to you. Right, and so what is the probability of this sample point specifically? What is the probability here? Well, on each trial, the probability of getting a success is P, and the probability of getting a failure is Q. Now, they're all independent, right? And so I can just multiply these things together, right? So the probability of this specific sample point is going to be what? So the probability of a success is P, and then another P, right? And how many of them? There'll be 8 of those. And then the failure, that's going to be 1 minus P, or Q. We'll denote it as Q just to be more succinct. And there's 12 of those. Okay, and so you can write that as P to the 8th power and Q to the 12th power. Okay, so that's the probability of this specific sample point, right? This one right here. Okay, now clearly the order in which we multiply these together does not matter, right? So this is actually the probability of any outcome with 8 successes and 12 failures. So this is actually the probability of any outcome with 8 successes and 12 failures, or 8 heads and 12 tails. Right? So then the next question is, how many such outcomes like this are there? Right? How many different ways can we get 8 heads? Right? You could get all 8 up front, like we've written here. Obviously, we could just as easily get all 8 on the back side, right? Those are different outcomes, right? So what we need to do next is we need to quantify all of the possible ways to get 8 successes. Okay. So how many different ways can we get 8 successes and 12 failures, or 8 heads and 12 tails? All right. So if you think back to our section on combinatorics and our counting section, you may remember this nice little piece here. N choose N1, N2. Right, so remember this was n factorial over n1 factorial, n2 factorial. Right, and so the idea here is you have n total things, and this tells you the number of ways in which you can get n1 and n2 different groupings of n things. So letting N1 denote the number of successes and N2 the number of failures. Right? We can easily see that N choose N1, N2 is really just N choose Y N minus Y, which is really just N choose Y, isn't it? Because N choose Y, if you remember, is N factorial over Y factorial times N minus Y factorial, right? And that's really the same format as this. So this format and this format are the same. And so instead of writing 20 choose 8 and 12, what we'll write instead is 20 choose 8. Right? When you only have two groups, then the other group just defaults. Right? So we'll write N choose Y. In this case, 20 choose 8. And so this is the number of ways to get 8 successes and 12 failures. All right, very good. Okay, so the event of getting 8 successes in 20 trials has this many sample points. Okay, so there's this many sample points that correspond to getting 8 heads and 12 tails. Okay, and so each of them has the same probability, right? What we saw above. And so really, when we say the probability that x is equal to 8, what we mean is 20 choose 8 times the probability of getting 8 successes and 12 failures, which is 0.5 to the 8th power times 0.5 to the 12th power. Okay, so this is the probability of getting any one outcome that has 8 successes. And how many are there? There's this many, right? And so you just add them all up. Okay, you add them all up. They're all the same, so it's really just multiply this number times that probability. Okay, all right, so let's generalize this. So more generally, okay, let's define the probability, the binomial probability distribution. So more generally, a random variable, y, is said to have a binomial distribution based on n trials and success probability p if and only if the probability of y is equal to n choose y times p to the y power times q to the n minus y power. And this is going to be for y equals 0, 1, 2, all the way up to n, and p between 0 and 1, of course. Okay. All right, so a random variable y is said to have a binomial distribution based on n trials and success probability p, right? There's your parameters, if and only if the probability of y is equal to n choose y, p to the y, q to the n minus y. Okay, so this would be the binomial distribution. Okay, all right. So that is, and you can kind of see how this, obviously, we kind of built this up in the case of our flipping a coin 20 times, right? So it's the same exact format here. So here's your p, here's your q, here's your n, and here's your y. In this case, x, we use x instead of y. Let's do an example where we just kind of apply this thing. All right, so example. What's the probability of getting 8 heads in 20 tosses? Probability of getting 8 heads in 20 tosses. Okay, And so let's say y is binomial with n equals 20 and p equals 0.5. And so we could say, in shorthand, we could say y is binomial, n equals 20, p equals 0.5, right? And so that tells us that, hey, if I want to know the probability of y for any particular y, I can just apply this formula. So the probability of 8 is going to be n choose y. I'm just going to write it out. P to the n and q to the n minus y. Okay, so in our case, it's 20 choose 8 times 0.5 to the 8th power times 0.51 minus 0.5 to the 20 minus 8 power. Okay, now sometimes these can be a little bit hairy to calculate because of the choose, but because of the factorials. But let's see what this looks like. So this would be 20 factorial over 8 factorial, 12 factorial, and then really it's 0.5 to the 8 times 0.5 to the 12, so it's really just 0.5 to the 20th. So I'll just put that together now. And that won't always be the case. It's just a special, it's just a coincidence here. Okay, and so we can see that this is going to be 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12, or times 13, all over 8 times 7 times 6 times 5 times 4 times 3 times 2, and then all that times 0.5 to the 20th power, right? And so you could go through and do some more cancellation, right? The 8 will cancel with the 16, the 7 with the 14, 5. You know, there's a lot of cancellation you can do here. But when you do all of that, you should get about 125,970 for the factorial here, right, for the choose function. What that means is there's 125,970 different ways to get 8 successes flipping a coin 20 times, right? So all of those are going to have identical probability, and that probability is 0.5 to the 20th power, right? So we're just going to multiply them out, and what we get is 0.1201. So about a 12% chance of getting 8 heads if you flip a coin 20 times in a row. Okay? Interesting, right? So you see how this binomial distribution, this particular form can be used kind of, ubiquitous. There's a lot of different scenarios where this binomial form is underlying the scenario. Just for practice, let's see, what is probability that y is equal to 1? Well, you can write it like that, or you can write probability of 1, right? And we know that that's just going to be equal to 20 choose 1 times 0.5 to the first power times 0.5 to the 19th power. Okay, and so 20 factorial over 1 factorial, 19 factorial, times 0.5 to the 20th power again. Right, how many different ways are there to get 1 heads? Well, there's 20, right? The head can be in the first position, the second position, ... the 20th position. So there's 20 different ways. So this all just equals 20. Okay. And so when we multiply all this out, we get a very small number, 0.00001907, right? So this is telling us that it is very unlikely that you flip a coin 20 times and get only a single heads, which squares with our intuition. We would expect about 10, right? So 1 would be very, very unlikely. Very good. Very good. Let's think of another example here. What about this? Let's say I roll a die, but instead of keeping track of evens and odds, I keep track of whether or not the outcome is a 5 or a 6 or something else. So what is the probability of getting a 5 or 6 on the roll of a fair die $50 times? out of 100 total rolls. Right, so I roll a die 100 times, and I keep track of whether or not the roll results in a 5 or a 6 or something else. Okay, and so basically what I need to do is I need to think about how I'm mapping this. So a 5 or a 6, I'm going to call that a success. A 1, 2, 3, or 4, I'm going to call that a failure. Okay, so what's the probability of a success then? Well, it's 2 out of 6, also known as 0.33. And what is the failure success or failure probability then? Well, that's going to be 4 out of 6, which is 0.67. Okay, so you see how even though the outcome of each trial has one of 6 potential outcomes, I can classify it into two buckets. I can call a success a 5 or a 6. I can call a failure everything else. Right, so I really have 2 possible outcomes. I'm either going to get a success or a failure, and the probabilities in this case are not the same. Right, so I'm more likely to get a failure than I am to get a success on each roll. Right, so that'll be very important. Okay, and so then let's let x be our random variable. We'll let x denote the number of successes out of 100 total rolls. All right, so x then is a binomial random variable. N is equal to 100, and p is equal to 0.33. All right. Okay, so what we're interested in is we want to know the probability of getting a 5 or 6 on 50 of the 100 rolls. So we really need to know, what we want to know is the probability that x is equal to 50. So that's P50. And so that is going to be 100 choose 50. So how many different ways are there to get, a 5 or a 6, right? How many different strings correspond to this outcome of 50 successes, right? So 100 choose 50, and then it's P to the n power. So P is 0.33, N is 50, and then Q to the n minus y power. Okay, so in this case, n minus x power. So it'll be 0.67, and then it's 100 minus 50. Okay, so the form here, I think I might have said it wrong. I want to make sure I'm right. So n choose x, p to the x power, and then q to the n minus x power, right? And so n is 100, x is 50. P is 0.33, x is 50, q is 0.67, n minus x, 100 minus 50, right? So that's the form. Right, and so this one we can work out, right? And so we get, just kind of expanding this is 100 factorial over 50 factorial times 50 factorial, okay, times 0.33 to the 50th power times 0.67 to the 50th power, right? And these are very big and tiny numbers, actually, right? So this number is enormous, and I'll just write it out for you just so you can check it. But you get 1.089 times 10 to the 29th power, enormous number of possible combinations. The success probabilities are 0.33 to the 50th. That's going to be 4.12 times 10 to the negative 26th power. And then the failures, when you 0.67 to the 50th power, that's going to be 2.39 times 10 to the negative 9th. Right? And so you're going to obviously want to use a calculator to get to all these numbers. But when you do this, you get 9.9 times 10 to the negative 6th power, which is really just 0.00000099. Right? And so it's a very small chance, actually, of getting exactly 50. Right? Now, why is that? I mean, we're basically saying we get a success half, what we're wondering is, what's the probability of getting a success half the time? Well, we're saying it's very small, actually. Why is that, though? I mean, if in the previous experiment we saw that that's probably would have been a large probability. In this case, this is a small probability because the probability of success is actually quite a bit smaller than the probability of failure. Now, if these were 50-50, then this would be much more likely, right? Also, the fact that there are 100 different outcomes, n equals 100, right, or 100 different, trials, that's also going to make any one trial less likely, right, than if there were fewer trials. Okay, and so this is the probability of getting 50 successes out of 100 in this exact scenario. Very good. Okay, so what does the histogram of a binomial distribution look like? Well, it'll vary greatly, actually, and it depends on the parameters. So let's draw a picture here. So let's say I've got n equals 10 and p equals 0.5. Then your histogram is going to look something like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are your y values, and this is the probability of y. The most likely thing if n equals 10 and p equals 5 is that you're going to get around 5. All right, so that's going to be your most likely. And then what it's going to do is going to drop off on either side of that in a sort of even way. All right, so it's going to look a lot like this. Right, so very symmetric, kind of centered around 5 and 6. And it's, it's going to basically have this sort of mounded shape. Okay, now the distribution will look quite different if we adjust the parameters. So let's say instead of n equals 10, p equals 0.5, we have n equals 10 and p equals 0.1, right? Meaning the probability of success is quite low. So in that case, if you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, the distribution will look more like this. All right, so it'll kind of drop off here rather quickly. Right, and so the idea here is that it's in the case of the probability equaling 0.1 for success, and the number of successes in 10 trials is going to be more likely to be 2, 1, 2, or 3. It's going to drop off really quickly, and it's going to be highly unlikely that you'll have 10 successes in 10 trials, right? And that makes sense because the probability of success is 1 in 10. Not, that's a very small probability of success. Okay, and then everything in between, right? So obviously if I make the success probability 0.9, then the skew will be in the opposite way. It'll be the opposite side, right? This would be n equals 10, p equals 0.9, right? Instead of looking like this, it'll look more like that, right? And then there's everything in between, okay? All right, very good. Very good. Now, where does the term binomial experiment come from? Well, it comes from the fact that each trial in one of the two outcomes, all the probabilities are actually the terms all come from the binomial expansion, right? So we've seen this binomial expansion before. Right? If you're taking this class, you've definitely seen this. If I have q plus p to the nth power, it's a binomial. If I expand this, then I'm saying it has this form. Okay, and we can see this really easily if we just do like n equals 2, for example. So for n equals 2, let's see what this looks like. So q plus p to the second power, and that's just foiling, right? Q plus p times q plus p, and you would get q squared plus 2pq plus p squared, right? Which, if notice the coefficient here is 1, so that's like 2 choose 0. And the coefficient here is 2, so that's like 2 choose 1, and it's p to the first power, q to the first power. And then over here the coefficient is again 1, and so that's like 2 choose 2. Okay, right, so obviously here you've got q to the 0, and you've got p to the 0. right? So you can see this kind of fits the pattern of this up here. And further, you can see this is obviously fits the pattern of the binomial probability distribution, where it's n choose y, p to the n, or p to the y, q to the n minus y. Okay. Another thing to note here is that the sum over all the y's of p to the y is equal to 1. And we can see this by using this fact up above with the binomial. So let's take a look here. So if I take the sum over y of p to the y, well, that's equal to the sum from y equals 0 up to n, the number of trials, and then it's n choose y, p to the y, q to the n minus y. Okay, now what is that? Let's write that out. So that's n choose 0. Right, n choose 0, p to the 0, q to the n, plus n choose 1, p to the 1, q to the n minus 1, plus so on, all the way down to n choose n minus 1, p to the n minus 1, q to the 1, plus, and the last one, of course, is n choose n, p to the n, q to the 0. Okay, and we know, right, this is the binomial distribution, but we know when we look at this, like, oh, hey, this is the binomial expansion, right? And so we know that this is equal to what? This is equal to p plus q to the nth power, right? Now, of course, p and q sum to 1, so this is just equal to 1 to the nth power, which is, of course, 1. Okay, so note here that p plus q equals 1. Right? And so this is how we can kind of use the fact of the binomial expansion to show that the binomial distribution does indeed sum to 1 if we sum over all the possible outcomes, all the possible values of n, or possible values of y, apologies. Okay, let's take another example. Let's look at an example that is a little less dicey and heads and coin flippy. Let's suppose that a group of 5,000 fuses contains 5% defectives. So suppose a group of 5,000 fuses contains 5% defectives. Okay. If we sample 5 fuses, let's find the probability that at least one is defective. At least one is defective. Okay, so suppose a group of 5,000 fuses contains 5% defect. So you get a huge group of, 5,000. 5% of them are defective. Now we're going to randomly sample 5 of them, and we're going to find the probability that at least one of them is defective, right? And so let's let x equal the number of defective fuses in 5. Okay, and so we're saying that x is binomial with n equals 5 and p equals 0.05. Okay, so if I select 5 fuses, there's a 5% chance that one of them is defective. Okay, and this kind of works in this setting because we're sampling from such a huge collection, right? There's 5,000. If you were sampling from like 10, it might be you couldn't really do this, right? But because there's so many to start with, and we're only selecting 5, we can assign this probability of 0.05 to each of the fuses in the sample. Okay, so what are we looking for? We're looking for the probability that x is greater than or equal to 1. Right, at least one is defective is what we're after, right? And so we could do that, kind of, straightforward. We could say, what's the probability of 1 plus the probability of 2 plus dot, 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 plus the probability of 5. But each of these is going to be like, 5 choose 1, 5 choose 2, 5 choose 3. And you're going to have all this computation to do. And it's just easier instead to say this is equal to 1 minus the probability of 0, right? So if I'm interested in 1 or more, I could just as well say 1 minus the probability of none of them. Okay, and so that's equal to, that one's straightforward to calculate, 1 minus, and this is binomial, so it'll be 5 choose 0 times p to the 0, q to the 5th power. P here is 0.05. 0.05 to the 0 power, and 0.95 to the 5th power. Okay, and so this is what? This is 1 minus 5 choose 0. There's only one way to do that, right? Right, so that's a 1, and this is also a 1. And this is 0.95 to the 5th power. Okay, and so we can do this math. This is 1 minus 0.95 to the 5th power, which is 1 minus 0.774, so this is equal to 0.226. So there's about a 23% chance, 22.6% chance of identifying a defective fuse if I select 5 out of this batch of 5,000. Okay, very good. Let's try another example. This is kind of a voting example, also very common application here. So suppose that 40% of a large population of voters supports candidate Jones. So 40% of voters support Jones. Okay, we sample 10 voters and we want to identify the number favoring Jones. So we sample 10 voters. We sample 10 voters and wish to identify the number favoring Jones. Okay, so let's find the probability that 6 support Jones specifically. That would mean Jones has like majority support, right? All right, and so we'll say that X is the number of voters supporting Jones out of 10. Okay, so we sample 10 and we let X denote the number of voters from that 10 that support Jones. And so X would be binomial and N is 10 and the probability of supporting Jones is 40%, so 0.4. All right, so N is 10 and P is 0.4. Okay, so then the probability that X is equal to 6 would just be 10 choose 6, right? And then it's P to the X, P to the Y, or P to the X, it's P to the 6th power. So 0.4 to the 6th power times 0.6, which is our Q, to the 4th power. Okay, and you can crunch these numbers. But when you do crunch these numbers, you should get 0.1116. Okay. Right, so again, this kind of works because we're talking about a large population of voters. So 40% of a large population of voters support Jones, right? And so we're going to just pull 10 of them out of this large population. We want to identify the number favoring Jones, specifically the probability that 6 of the 10 support Jones, right? And so in this case, X can be modeled using a binomial distribution. All right, very good. So that is what the binomial distribution is all about. That's the kind of how you construct the binomial distribution in your head, how you should think of the structure, the probability, the pattern of randomness that underlies the binomial distribution. Remember, it's identical, fixed number of trials. All of them are independent, right? Coin tosses, rolling dice, randomly selecting voters from population, etc. They're all independent, right? Two possible outcomes, right? Two possible outcomes for each trial. And what we're interested in with the binomial distribution is the number of successes in a fixed number of trials. And basically that structure can wear an infinite variety of clothes, right? In the real world, there are an infinite variety of situations and scenarios that have underlying it this probability model, this binomial distribution probability model. Okay, we just hit on a few examples, but there are obviously infinitely many. So now let's kind of turn our attention to identifying the mean and the variance of this distribution, right? Because every time we introduce a distribution, we'll do this kind of same thing. We'll lay out what it looks like. We'll try to derive the probability function. We'll look at the histogram. We will do some examples. And then the last thing we'll want to make sure we understand is what's the mean and what's the variance, the standard deviation of the distribution. So, theorem, if we let y be a binomial NP random variable, then the expected value of y is equal to, well, we'll say mu, which is the expected value of y, is equal to n times p, nice and simple. Then, you know, the number of trials times the probability of success, that's the mean, very nice. And the standard deviation, or sorry, the variance, which is the variance of y, is going to be equal to n times p times q. Okay, very nice. So these are very simple expressions for the mean and the variance. So let's go ahead and prove this. This will just take a second. I think we'll just prove the case of the mean, right? But this one could also be done. It's not completely trivial, but I'll leave this one to you, and you can look it up, or if you want to take a stab at it, that's fine. But let's go ahead and prove this side of the thing. Okay, so whenever you're trying to derive, or prove the mean or the variance of a distribution, you just want to start by kind of writing it out. So the expected value of y is equal to the sum over all the y's of y times the probability of y. Right, now in the case of the binomial distribution, we have an explicit form for the probability of y, and so that is the sum from y equals 0 to n of y times n choose y times p to the y q to the n minus y. Right, so that's the probability distribution function for a binomial distribution. Now, here's where it kind of gets tricky typically, right? So let's note here that when y is equal to 0, the term is 0. So note, if y is equal to 0, then the probability of y is equal to 0 times n, so sorry, y times the probability of y. So this thing here, when y is equal to 0 times n choose 0 times p to the 0, q to the n, right? And no matter what this is always going to be 0, right? So given that fact, we can re-index this, and we can say that this is equal to the sum from y equals 1 up to n of n choose y, of y times n choose y, p to the y, q to the n minus y. Okay, so all we've done is basically remove the bottom term here. Instead of 0, it starts at 1, and that's because the first term is 0, so we can leave it off. Okay, now let's go ahead and expand this thing a little bit. So this is equal to the sum from y equals 1 up to n of y, and now instead of n choose y, we're going to actually write it out. It's n factorial over n minus y factorial times y factorial. And then this is p to the y, q to the n minus y. Okay, and we can rewrite this again as the sum from y equals 1 up to n of n factorial over n minus y factorial times y minus 1 factorial, p to the y, q to the n minus y. Okay. Now, if you notice, we can factor an, so there are going to be n terms here, right? We can factor an n and a p out of each of these terms. Okay, and so when we do that, we get n times p, right? And my sum stays the same, y equals 1 up to n. And it's going to be n minus 1 factorial, where I'm taking an n out of each term. And then it's going to be, down below, it'll be n minus y factorial and y minus 1 factorial. And this will be p to the y minus 1, and then q to the n minus y. Okay, now what we're going to do is a nice little trick that we'll use a lot of times in this class, and that's going to be, we're going to change the variable. So we're going to let z equal y minus 1. Now the reason we do this is because when we do this, we can see the structure of this summation a little bit more in a more straightforward way. Right, so this is equal to np times the sum from z equals 0 up to n minus 1, right? So z is equal to y minus 1. And we have on top still n minus 1 factorial divided by, now y is equal, so z is equal to y minus 1, so we can change this piece here, and instead it'll read n minus 1 minus z factorial, and then times z factorial, and then p to the z power, and then q to the n minus 1 minus z power. Okay, now notice here, this piece here, right here, so this is just the binomial probability function for binomial where n is n minus 1 and the probability of success is p. Okay, right, so this can be rewritten as n times p times z equals, times the sum z equals 0 up to n minus 1, and then this can all be kind of packaged up as n minus 1 choose z, and then it's p to the z, q to the n minus 1 minus z. Okay, right, and so that's what this is saying. All right, very good. So this is kind of a, kind of a busy derivation, but not too bad. Okay, so we've got, let's write this up here at the top of the page. So this is n times p, and then again we have the sum from z equals 0 up to n minus 1 of n minus 1 choose z times p to the z times q to the n minus 1 minus z. Okay, and then we said that this is just going to be the binomial n minus 1 p distribution. Okay, or the inside part anyway, the summation part. Okay, and so we know then that the sum from z, the sum over all the z's, whatever happens to be, in this case z equals 0 up to n minus 1, of the probability of z, we know that that sum is going to be equal to 1, right? And so we can kind of take that fact and apply that to this. So this whole thing here is basically just equal to 1. So I've got n times p, and then I've got the sum from z equals 0 up to n minus 1 of n minus 1 choose z, p to the z, q to the n minus 1 minus z. Right? This whole thing is equal to 1. So this is equal to n times p times 1, which is np. Okay, and so remember, we started by saying the expected value of y, right? And then dot, 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 we did a bunch of stuff, and so now we see that that's equal to n times p. right? So kind of a little bit of a tricky derivation, but it really is just, write out the definition of what the expected value is, right? We'll just write out what the definition of the expected value is, and then sub in your probability function, and then do some work on it, right? And similarly, you can identify the variance of the distribution, and so you can also show that the variance of y is equal to n times p times q. Okay, it's a little bit tricky also, but I think the same kind of tricks will work. Okay, very good. I think we'll end with that, and in the next lecture, we'll get into another distribution, this one called the geometric distribution. Very similar to binomial, a little bit simpler, I think, but similar, right? So similar in setup. Okay, until then, take care.